Hello, my name is Akulin, and I am presenting my Lab 2 motion of a falling object. Introduction. I dropped a piece of paper and recorded it to analyze the motion of the fall in the tracker application, and I compared my results to computational models. The purpose of this lab is to see the effect of drag on the object and compare my observations to calculations. This lab will show that accounting for gravity and drag will give a more accurate calculation than just accounting for gravity. The physics principles I used in this lab were Newton's second law and momentum principle. Newton's second law is F equals ma, and momentum principle is F equals delta momentum over delta time. I use these because there's a force acting on the object, and drag force is given by force drag equals negative b times velocity squared times the unit vector of v. I use this because the object falls slower than a rock at the same height, therefore there is a drag force. Drag force is the opposite direction of the motion, so if the motion is going down, the drag force is pointing up. And the force of gravity given by mass times gravity, because the object is falling, so acceleration is due to gravity. The forces acting on the object is drag and gravity. These are my results from the tracker video. This is the first computational model I built, and this is the one accounting for gravity and drag. This one was accounting just for gravity and no drag. And this one, drag force was given by negative b times v squared. And these are my results of the two computational models and what I analyzed in the tracker application. Analysis. Observed came out to be closer to the model that was only accounting for gravity, which is most likely due to human error in the tracker application, because the expected was that it'd be closer to the one with the drag force that accounted for drag force. But the shape of the curve of the motion is similar, but the model with drag did not fall as far in the same amount of time, or it took longer to fall the same amount of distance. What does it mean? When the drag force pointing up has balance with the force of gravity pointing down, the net force becomes zero, and that's when the object reaches its terminal velocity. This is best predicted by the model that accounts for drag force, where the drag force is bounded by the gravitational force. In the model without drag, velocity would keep on increasing as there's an acceleration and no drag force pointing up to counteract it and not reach its constant velocity. The terminal velocity would not change, but the time it takes to reach would be quicker, and terminal velocity depends only on the balance between, and that's because terminal velocity depends only on the balance between the drag force and gravity, which are the same for both scenarios. In my model, there is an initial velocity, but it reached the same constant velocity because there's a drag force that counteracts, so the terminal velocity does not change.